morning, and we have Alex Slivkins, who's a principalization and organization, talking about incentivized exploration.
Hello? Does the mic work? Okay, cool. Yeah, hi all, thanks for coming. I'm gonna do a survey talk on incentivized exploration. It's like line of work with a bunch of collaborators, and so now there is a survey in the textbook chapter. Okay, so what is this about? Well, the key question is this: how do you incentivize self-interested agents to explore when they selfishly prefer to exploit? I mean, here agents are like users in recommender systems, and of course, this is like a widespread application scenario because, you know, recommender systems are everywhere, and the ability to do good recommendations is essential in many platforms. So slightly more technically, it's going to be about, you know, bandits and agents. Even more slightly technically, it will be about bandits with evasion persuasion, and in a few slides, I'll explain what it means. So it's like, on a high level, it's like one nice way to combine exploration and incentives. And I just wanted to point out that there are several other interesting ways in which, you know, exploration plays out in strategic environments. And like one useful way to sort of tell these ways apart is to see like what is which aspects of the model are controlled by the agents. So say if agents control bids, that's like repeated auctions, and then like, you know, dynamic pricing, agents only affect rewards. In like platform competition models, like users may be choosing among platforms running Bandit algorithms. But in incentivized exploration, agents control the choice of actions. Okay, so let's dig in a little bit. So let's look at sort of idealized model of information flow in the recommender system. So what happens is that like a user arrives, needs to choose a product, okay, receives a recommendation and maybe some extra information like ratings and whatnot, and then you know, chooses a product and leaves some feedback. Well, so okay, what's going on here is that like on one hand, this user consumes information from the previous users through recommendations, and on the other hand, it produces information for the future users. Is the pointer visible? Okay, so you see, there is some exploit trade-off going on here, and for the sake of the common good, the user population would like to balance this exploration and exploitation. For example, they could be coordinated through a system's recommendation if a system could tell people what to do. Well, not quite, because incentives are misaligned, because self-interested users are like, you know, agents that would like to exploit rather than explore. And, you know, as a result, some actions may be explored at suboptimal rate, and, you know, some actions could remain unexplored, and like in the kind of idealized worst case, best action may remain completely unexplored if it seems worse initially. So like a bunch of things could go wrong. Okay, so let's put some more concrete model to this. So, okay, say we have T rounds and K actions, also called arms. In each round, what happens is that a new agent shows up, observes something, like whatever it observes, then chooses an arm and reports a reward. Well, let's keep things simple. Let's say that rewards are IAD, meaning the reward of each arm is drawn independently from some distribution specific to this arm, and this distribution is fixed over time, but is not known. And let's put a common Bayesian prior just to make sure that, like, you know, everybody's beliefs are well defined. Okay. Let's say the objective is social welfare, in other words, cumulative reward of all the agents. Like, what do the agents do actually? Well, a rational choice for each agent would be to choose whichever arm that seems best, given whatever the agent knows, in expectation of the prior. So, okay, that's what the agents do. Okay, that's kind of the model, but note that we left something unspecified. Pointer, I don't see the pointer. Okay, I'll show. So the message, okay, I do see it sometimes. Weird. So the message, what is the message? Well, the default is that each agent sees full history. And no, this is like, it corresponds to, I mean, seeing full history and making a rational choice corresponds to something well-known in Bandit. It's called like greedy algorithm, where like you don't explore, you just explore. Or more precisely, it's like Bayesian version of the greedy algorithm. Okay, what could go wrong with greedy? I mean, why don't we just do that? So again, in each round, this algorithm just exploits given the current history. So it's kind of instructive to see what goes wrong. So, okay, let's keep things simple. There are just two arms with mean rewards mu1 and mu2. And like, let's look at this like prior gap, like, gap between mu1 and mu2 and expectation over the prior. And let's say arm one looks better initially. Well, what's going to happen in round one is that you need to choose arm one. Okay, now let's keep things really simple. If rewards are deterministic, then mu1 is observed. But then if mu1 is better than prior mean reward of the other arm, then the other arm just never gets chosen. And this is like a big time learning failure. Okay, what about randomized rewards? Well, maybe, randomness in rewards would allow us to explore. Well, turns out no. In fact, like arm 2 is never chosen with some constant probability. And like the probability is actually the prior gap. And this is also kind of a big time learning failure. And in particular, one could show that like Bayesian regret of this algorithm is going to be linear in time under some mild fine print. Interestingly, like you'd think such result would be known for many decades, because like it's like, why do I need to explore? And I thought so too. And at some point I needed it and I looked around, I couldn't find it. I asked around a lot, I couldn't find it. I tried to prove it, I couldn't prove it. And it was kind of worrisome. And then I asked Mark Selkin, he proved it. So like now it exists. Okay, so let's go back. Okay, we really need to explore, we really need to incentivize exploration. Okay, so how do we incentivize agents to take actions that seem suboptimal given like their initial biases and given what the algorithm knows now? Well, there are some external incentives, like one could offer payments or discounts, or one could promise, higher social status, like you'll get a merit badge if you do a good job, or just some people just like to experiment. Well, one could rely on any of that, and it's fine, but like it's prone to selection bias, right? And just like, I don't know, the people who will explore will be the people who are more sensitive to money, or who are like more vain, or who are more like adventurous, right? And it's also just not always feasible because maybe you don't have money or something. Okay, so that's not what we do. And instead, our approach is to create information asymmetry by not revealing full history. And then we like use that information asymmetry to create incentives. In other words, the algorithm will know more than any one user. Okay, so let's go back to the model. That's exactly what we had before. So there are like messages. The default was full history, but it doesn't work. So instead, what do we do? Well, now the messages are going to be chosen by the algorithm. Okay, we can actually simplify it a little bit. So one can prove that without loss of generality, the message could be just a suggested arm. And then the whole algorithm will need to satisfy a condition called Bayesian incentivized compatibility, Bayesian incentive compatibility, which essentially says that each user is better off following recommendations. So, okay, and now the model got kind of simpler in that, like, It's just a Bandit algorithm with an extra constraint, and the constraint is about incentives. And conveniently, what we can compare like what happens with these BIC Bandit algorithms to what happens with just like Bandit algorithms. Okay, and there is a bunch of work on this over several years. The home community has been mostly ACM-EC, and I mean, it's kind of hopeless to expose the stuff linearly, so instead I will sort of dissect it in several different ways in the rest of the talk. And like I will touch upon these papers. You know, I'll be glossing over a bunch of stuff. Okay. And by the way, do ask if something is or not. Okay, I have a wonderful plan for the rest of the talk, which consists of related work, basic stuff, advanced stuff, and open questions. Okay, so I think it's kind of interesting to see, like, to kind of zoom out a little bit and see where incentivized exploration sits in the, well, slightly grander scheme of things. And it happens to sit at the intersection of bandits and two sort of important sub-areas of economics, or theoretical economics, social learning and information design. So social learning is like agents learn over time in a shared environment. And typically there is like no principle, and like agents are there on their own. Most related, like there are like many models there. The most related one, called strategic experimentation, posits that like agents are like long-lived, like learn over time. Each agent can explore and exploit, but of course each agent prefers to free ride on exploration done by the others. Like they derive optimal policies in a very scary way and like analyze. Anyway, compared to all this work, what we do can be framed as like social learning with a mediator, because like, you know, we have a bunch of agents in a shared environment. Collectively, they need to learn something, and there is a mediator, the algorithm. As far as information design, see, one round of our model is this very well-known model in theoretical economics called Bayesian persuasion, of which I guess many of you know. So in a nutshell, a sender gets it's like a game between two players, sender and the receiver. Sender gets a private signal, chooses a message for the receiver, and then like receiver observes that and chooses an action. And the sender wants to get the receiver to choose like what sender wants. The focus in that work is usually on like deriving optimal policies for this one round game. I mean, optimal for the sender. In comparison, so for us, the sender is an algorithm, and the signal is the history of the algorithm up to this round. The objective is different. The objective is like, you know, our objective is like trade-off, explore, and exploit. So one could sort of fit it into the model of Bayesian persuasion in a kind of very myopic way. It's like, what if initially arm1 is preferred and all we want is to try arm2 in the next round? Well, then we could say, okay, what if the sender's utility is just 1 if arm2 is chosen and 0 otherwise? So it kind of maps. But a long-term objective of explore-exploit trade-off, it doesn't seem to fit into the standard model here. So in other words, we do something different, although related. Okay, let me mention kind of 3 closely related lines of work. One line of work recently is about how like greedy algorithms sometimes work pretty well, but you need to assume some structure. It's like kind of strong assumption about structure. For example, like linear rewards and like very heterogeneous agents. And in a way, this structure that you assume, it kind of substitutes for explicit exploration. Another line of work is like, okay, you like we incentivize exploration through information, but you could do it with money. And like there is very nice line of work on that. And in all this work, all agents observe a full history. So like the only lever in this work with which they incentivize is the money, whereas for us, the only lever is information asymmetry. And finally, online Bayesian persuasion, on which there was a talk earlier today. It's kind of another model combining online algorithms like over time and Bayesian persuasion in each round, but it's kind of very different. The key distinction, I think, is that in each round the signal of the algorithm is IID, whereas for us it's algorithm's history, so it's like it changes over time and kind of grows over time depending on the algorithm's actions in the past. Also, to my understanding, like what makes this problem interesting and non-trivial is the incentives. So it's like without incentives, there is no problem. It's all about like incentives. And for us, of course, if you remove incentives, what's left is a bandit problem. Okay, so let's go do some basic stuff about our model now. So it's let's kind of ground ourselves into some technical bit to see that there is like something immediately non-trivial going on top of bandits. So let's look at the prior and let's observe that in general, it's like for average, like there are priors for which the problem is completely hopeless in the sense that like you will never try ARM2 ever. For example, if like ARM1 looks better initially, and like the prior is such that mu1 and mu1 minus mu2 are independent. Well, initially you need to try ARM1, fine, but like no matter how much data you get about mu1, you will know nothing about mu1 minus mu2. So you will never try ARM2. Okay, it means that we need some assumptions on the prior. So as we prove, there is a sufficient condition for two arms, which basically says that like if we have enough samples of ARM1, ARM2 can become the best arm. So to make it slightly more technical, it's like let's look at something called posterior gap, which is like gap between the two arms in expectation over the samples. So in expectation given the samples. So it is a random variable. And the condition is that this random variable should be strictly positive with some positive probability. And like under this condition, we can explore ARM2 as it turns out. Moreover, this condition is necessary. It's like without it, we actually will not sample ARM2. And there is well, not that it's super important to the stock, but the proof is very simple. It's like you could, massage expectations and see if, if it's false, the AC condition will never work in our favor. Okay, and now it's for two arms, we know exactly what's going on. For more than two arms, it's not quite clear. We have a kind of similar condition, which is sufficient. And this condition includes sort of the paradigmatic case when the prior is independent across arms and rewards are bound and they might have full support. So it's like, okay, in the paradigmatic case, we can do stuff. Okay, what are the basic techniques? So I guess usually people talk about like rewards then techniques. I will switch the order. Like, what can we do in this setting? Well, the most basic and like simultaneously the most general thing one could do is something called hidden exploration. So the idea is that we hide a little bit of exploration in a whole lot of exploitation, right? Well, precisely in each round, we like, go wild, do whatever we want with some small probability that depends on the prior. And otherwise, we exploit given what we know. And the point is that like the agent doesn't know which branch we're in. The agent knows that like most likely we exploit, and we exploit given more information that the agent knows. So kind of there is a possibility that the agent is in the exploration branch, but on the balance, it's better to follow recommendation. And like one needs to adjust the probability, kind of make it low enough to make that happen. So in fact, this is a general reduction in the sense that like one could take any algorithm and like, instead of this go wild step, just like, I mean, the most basic version is just like play arm2, but actually one could take any algorithm and like when you like go wild, it like advance a step of this algorithm. So you kind of take an algorithm and make it BIC, but you lose because of this factor. Okay, another technique that works is this well-known algorithm called successive elimination. The idea is like you maintain a set of active arms, you iterate among them until you can eliminate one of them with high probability, and then you continue. However, one needs to modify it to kind of make the confidence bounds larger because of incentives, and like because of that, you kind of lose in the performance a bit. The benefit of this algorithm is that it does not need to know the prior. Like it's possible to like make it happen if you only know like 2 parameters about the prior and like only know them approximately. So it's like, in reality, you don't really know the prior, and the prior is kind of fictional anyway, but it suffices to just know these parameters, and then like, this algorithm would handle any prior that sort of is consistent with these parameters. And in fact, different agents could have different priors as long as they're consistent with these parameters. Okay, and finally, Thompson sampling works as is, which is like cool. It's like a standard algorithm, it works. If the prior in Thompson sampling is the actual prior. Okay, some caveats. Well, the last 2 algorithms, successive elimination, Thompson sampling, they really need independent priors. And like beyond that, we need to go back to hidden exploration. Another caveat is that each algorithm needs some initialization. So it needs to be initialized with some amount of data, some number of samples of each arm. However, that number of samples depends only on the prior. So it's like, the way we usually think about regret bounds is like a function of time, of the time horizon. Well, this is like a constant in the time horizon. It depends only on the prior. And the way we collect that is by a version of hidden exploration. Okay, so with these techniques, what do we prove? Well, okay, we can use hidden exploration and get optimal Bayesian regret. Well, okay, optimal in time for a constant number of arms. It is exponential in k the number of arms, which could be just the price of exploration, like could be the price of incentives. It's like, for bandits, it's like root of kt, but now it's exponential. But I'll get to that in a little later. But in t, it's optimal. For independent priors, we could get optimal frequentist regret using successive elimination. And again, it's like optimal in time for a constant number of arms. And with Thompson sampling, we could get optimal Bayesian regret, like really for any k, except, well, we need these initial samples of each arm, and to collect them, we again need to pay something. Okay, so that's the basic stuff. Yes, sir.
Elimination beginning the initial samples as well, or
yes. And we need to like blow up the confidence bounds quite a bit. Okay, we can go to some advanced stuff, and like which questions can we ask? Well, turns out there are a bunch. Even in the basic model, we could ask, okay, what should really be the dependence on the number of arms and the prior? And like, okay, the dependence on the prior is like, which parameters should we be thinking about? Also, like, just like in usual bandits, we could think about regret, or we could think about pure exploration. So like here, the goal of pure exploration is to explore, all explorable arms. That is like all arms that it's like, it's not necessarily true that any arm can be explored by a BAC algorithm. So it's like some arms they can't, but we want to explore all arms that can be explored. Now, like on top of that, we could extend the like learning model underneath the problem. So like so far it was kind of the most basic model of bandits. Well, okay, we could ask how about the more complicated problems? Like what if we have extra feedback like in contextual bandits? Or like what if the problem is like a large structured horrible thing like episodic RL, for example? Thirdly, we could talk about extending the kind of economic part of the model in several ways. Like, what if agents are heterogeneous? I mean, say, like, what if agent has a type which is like private or public, whatnot? We could ask many questions like that. What if there are multiple agents in each round and they play a game affecting one another? For example, if it's like Waze recommends driving directions to agents, well, drivers affect each other on the road because they create congestion. And thirdly, like we make kind of standard but very strong economic assumptions that if you think about them, they're kind of iffy. And like, what if we try to relax them? Okay, so in the rest of the talk, I will touch upon, like one example of, these three things. How am I doing on time, by the way?
17.
Oh, awesome. Okay. So, in the basic model, it's like, let's ask, okay, what is the price of incentives? In other words, like, what is the loss in performance in some sense compared to optimal algorithms in bandits without incentive constraints? More specifically, let's focus on kind of pure exploration or like sample complexity question. So like, how many rounds do we need to explore each arm once? In a way, it's like the most basic question you could ask. Forget about regret. I just want to see each arm once. And okay, let's simplify things. There are like independent priors, and like, for each arm, the prior comes from some family of priors. So one result is that is about like exponential versus linear dependence on k, the number of arms. So remember, in the basic results, we were getting exponential dependence. And like, it was not clear, is this really a price of incentives or not? Well, it turns out there is a sharp dichotomy. So like, depending on that family, the kind of optimal number of rounds here is either linear or exponential. It's like nothing in between. And for a sort of standard examples you would think of, it's actually linear. It's like beta priors or truncated Gaussians. It's like, the first and main things you would think of when you think about Bayesian inference, it's linear. Okay, but how do things depend on the beliefs in the prior? Well, what is the right parameter? It seems to be in some sense, the strength of the beliefs. It's like, how strong is my belief that the mean reward of this arm is approximately this. Well, it's all about the variance of the prior. So roughly, it's like, look at the smallest variance. Well, that's kind of the key parameter. Well, it turns out that it needs to be exponential in that. So it's like not good, but it has to be that way. So that's really the price of incentives. And like, note that all this complexity happens even with like basic bandit problem with two arms. Okay, the algorithm that achieves that is kind of tricky. It's kind of like starts with hidden exploration, but then in hidden exploration, there are like two branches, explore, like doing whatever you want, or exploit. Here, there are three branches: explore, exploit, and some kind of a secret sauce third branch combining both in some fairly tricky way. And crucially, the kind of aggregate result of that is that the exploration probability increases exponentially over time. And that's the key driver that like allows us to get from like exponential dependence in hidden exploration, exponential dependence on K in hidden exploration to linear dependence. Okay, that's that for this extension. Yes.
Can you comment on dependence? You're assuming independent priors, all these results.
Oh, yes. Well, we need to assume that the priors are independent across actions. Otherwise, we cannot do this. Without independence, we can do something. We can do hidden exploration. And like for two arms, we have a nested insufficient condition, like I said. So it's like, we know exactly what's going on, and we can do it when we can. It's like when it is at all possible, we can do it. So that's the statement. But does any of this stuff extend beyond independent priors? It's unclear. It's also not very clear how to even formulate the result, because like with independent priors, you could sort of tease apart the K out of dependent priors. But if priors are dependent across arms, it's not as clear. Okay.
When you talk about dichotomy, do you mean that there is a characterization of which distributions submit linear and everything that does not satisfy will be?
Yes. There's a condition, and it's linear, and like if not, it's exponential. Let me give example of another extension, like when we extend the learning model, right? So specifically, let's tackle kind of a paradigmatic hard learning problem of incentivized of episodic reinforcement learning. And like most of you know what episodic RL is, so and like I can't like really like explain it properly, so I won't even try. It's all about MDPs, and what happens in our model of it is that in each episode a new agent arrives, observes some message chosen by our algorithm, and then chooses a policy in a self-interested way, and that policy stays for the entire episode. So we only tackle a pure exploration version, which is like, visit all things, loosely speaking, that can possibly be reached by some RL algorithm. So it's like, we just want to visit everything that can be visited. Okay. What makes it complicated is that, like, from the point of view of like incentivized exploration, the actions here are policies, and there's like a huge number of policies, and policy values are really correlated. So it's like, it makes it complicated. We'd like to avoid exponential dependence on the policy space, for example. So we do something here which kind of avoids that very dependence. And like the details of the results are kind of tedious, but let me mention a technique which is a little more interesting, which is something that we call hidden hallucination. So here, essentially, the message is algorithm's history, and like in each episode, like most of the time, we show true history. So then the agent exploits or can exploit. Or else we show kind of a hallucinated history. So it's like we artificially generate rewards to promote exploration. Namely, we just look at like all the stuff that was visited before, and we make it look bad. The key point here is that like we're not telling the agents exactly what to do. We just tell them, hey, try something new. Same reason as for hidden exploration, is just like most of the time it's exploitation. So on the balance, the agents want to follow recommendations, but they every once in a while they will explore. The technical details are kind of very hairy. Hidden exploration, but it's kind of a property of reinforcement learning. Any proof there is complicated for some reason.
If the objective is pure exploration, why exploit at all?
Why?
Why exploit with probability 1 minus p?
Okay, good. So it's the objective of our algorithm, but we need to create incentives for the agents. So each agent wants to exploit. So it's like each agent will exploit given whatever message that we show them. But why would the agent trust us? Well, most of the time we show full history. So,
Isn't that just a nice property of the algorithm? Or
yeah, it's not what we need per se, just like a means to the goal. Yeah, but yeah, the goal is pure exploration. Like one could use that data to exploit afterwards and get something like t to the third degree.
So statistically, it should look like plausible.
Oh yes, exactly.
Is that
That's
easy
a
to
great
do or
point.
something?
That's a great point. So most of the complexity technically here is that we need to make it look plausible.
So you said that you don't talk about
We don't, as long as it's new.
okay.
That's like what allows us to to get around the fusion of the process.
Okay. So here you reveal a history as opposed to like a name of policy. Is there a difference between those two?
Well, in theory, it's the same thing because, like, in theory, there is like a version of revelation principle. Thanks for asking this question. And, like, without lots of generality, like, you can recommend. It's just so in that sense, it's like a convenient way of representing this algorithm. That said, that argument requires like knowing the file, doing integration algorithm. So it's like an algorithm could potentially do that, but it's like this is an extra representation.
Is there, like, following up on such point, is the a reason of like thinking about the representation of the methods, and you don't want to have something that takes all states and all actions and like a policy has a representation complexity that maybe
so here is just a community representation. And like whatever I say about like sorry, here is just a convenient representation for the truth. Anything that I say about like, it may be more convenient in practice is just kind of like there is no deep underneath, except that's a nice segue to the next extension. But let me see if there are more questions.
Questions, maybe something should please go ahead. I mean, I see why this is a nice representation, but now the independence between agents is really important. Agents could talk to each other. If there is
Yes. Right.
Whereas with revelation, that's not true. Agents could communicate and it could be worse, but it's
So, in general, if you like even in the Bandit model, it's very important that the algorithm controls the flow of information. And like, if there is some information that like escapes and is observed by the agent, no matter what, it really messes us up. What I mean, like, there are ways to deal with that a little bit, but you know, it's a big headache. But very soon it doesn't happen. So the third, I don't know for sure, but to the best of my knowledge, it happens to be the first paper that combines the relevant mechanism design. A third and final extension that I wanted to talk about is about relaxing economic assumptions. And like, they're kind of standard and we don't even think about them. It's like, okay, but then like if you think about it, so, okay, there is this thing called power to commit to the algorithm. It's like the, you know, principal can commit to whatever it's doing. And like, you know, it's kind of iffy. It's like, do I, like, it's more than that. The agents like need to know the algorithm to do Bayesian update. And like, do I know the algorithm? Do I trust the platform to like implement the algorithm that they announce? And like, even if they want to do it, do I trust them to like not mess it up? I actually don't trust them. Then like, there are cognitive limitations. It's like, you know, want agents to think about Bayesian updates. So can they do it? Like, do I as a user want to do it? I don't want to worry about it. I mean, one way to like mitigate that is to think like, oh, you know, somebody else will tell me that there is a proof. There is a proof and you need to follow recommendations because, you know, such and such theorem says that the algorithm is BIC. But I mean, will I trust that proof as a user? Like, probably not. And like, I won't even understand what it is. So it's like kind of iffy. Moreover, there is the thing about rational choice. It's like, you know, I assume that people just optimize expected utility, but like, what if they don't? There is a whole lot of stuff about like risk aversion or like soft max versus hard max. Also, sometimes people may be averse to being experimented. It's like, you know, maybe it's all, you know, BIC, it's all, you know, I'm supposed to follow it, but I just don't like it. So I will just leave the platform. So, okay, in the face of all that, how do you ensure a predictable user behavior? It's like, you know, we'd like to know what the users are going to do and somehow control. And like, there is no like great answer set in stone, but like we try something. So here is an attempt through selective information disclosure. So it's like this, like users want to, what the users want is to see the full history. Right? Well, okay, that's too much, it doesn't work. Let's try to give them the next best thing. So kind of some history, but not full history. More precisely, the principal chooses a partial order on rounds. In other words, a directed acyclic graph on rounds. And, you know, each user sees a full history of her branch. So it's like, you know, I see what happened to all the rounds that, you know, precede me in the partial order. So it's kind of nice in that this history is like, this sub-history involves a subset of rounds that is fixed over time. So it's like no cheating. I mean, a cheating would be like, you know, I want a user to try ARM2, therefore I subsample all rounds which make ARM2 look good. Oh, okay, I'm not doing that. I need to fix all the rounds in advance. And moreover, it's like the history that each user sees could be interpreted as like the full history of the relevant part of the algorithm. It's like the rest of the world, you know, just some other stuff happening in the world doesn't concern me, but the part of the algorithm that actually concerns me, I see the full history of that. So the nice, well, one nice thing that happens to economic foundation here is that we only need to assume what users do when they see full history, as opposed to like what users do when they interact with some crazy algorithm. Also, also regarding hard max versus soft max, well, we could handle either as long as it's consistent with confidence intervals. So, okay, we construct some such order, and the key is to construct this order in a very intricate way. But like after it's done, you know, the principal is not doing anything, and just kind of agents kind of learn on their own. And you know, even though each agent is sort of locally greedy, it follows kind of a greedy algorithm locally, but the whole thing works in the system explorers. And one could do kind of relatively easy construction to get kind of non-adaptive exploration and like T to the third regret, or like much more tricky construction and get root T regret. How much time do you have left? Cool. Let me conclude with open questions. And to refer to what Ilan said in the yesterday's panel, I'm not promising, you know, best works in operations research, but I think they're pretty interesting. Or I think so. Like one thing is about relaxed economic assumptions. So it's like, do we have the right ones? And like, what does it even mean to have the right assumptions? Also, like our constructions are pretty complicated. Can we make them like simpler and like less brittle, right? Then, okay, what if the prior is not fully known, or like initial, and like maybe what if we can like refine that knowledge over time? Thirdly, well, we assumed short-lived agents. You know, each agent only lives in one round, not because it's what happens in life, but because that's what we could handle. Like, but like, what if they're like long-lived, right? Next, you know, as you said, like, what if there are inevitable observations? And there is a little work on that. Well, some work on that, but like it's still complicated. And finally, like with heterogeneous agents, like which like we know something, but like which regret bounds, it's not clear. And like it's plausible that like diversity of agents can be used to help basic exploration rather than just make our life difficult in the proofs. So it's like all that stuff is still pretty open. Okay, thank you.
Questions?
Optimize over that. How flexible is the
Oh yeah. Not. It has to be, well, okay. A simple construction that gives you explorer at first is somewhat robust. It's like, there are ways you could mess with it and it stays useful. But the big construction that gives you two-regret, we don't know how. It's like, can be relaxed like slightly, but it's pretty better. We don't know how to make it. So, in fact, to me, it's not a question. So, yeah, how would we make it? It's kind of a proof of concept. You can do it.
Okay, thank you.